My name is Asfand Yarkuhi, and I will doing the presentation on analysis of a wind loading on a structure for today using SolidWorks simulation tool. All right, what we are covering in this session is about fluid structure interaction, its definition and method. So that is the scheme we are going to use. And then we are going to focus on SolidWorks fluid and structural coupling methods we have and explaining what the procedure look like. We will continue our presentation with a case study. Well, the model of telecommunication antenna has been selected to do the FSI analysis. In this regard, we first start with the flow analysis setup as an external flow over the object. We will introduce the parametric study. Well, we have different attack angle with the antenna unit against the wind load, and we will introduce how we can set up multiple studies. Since we have done the setup and pre-processing stage, we are going over the result, and SolidWorks Flow Simulation has a special tool and tab for comparing the result. As far as we finalize the flow, it's the time to export the result to our FEA study. And then because of the structure we have, we are introducing different meshing technique and also different element types such as solid, shell, and beam elements. And we will introduce how we can use all of these three elements in one model. We will introduce local contact set, and also using one type of connector, which is edge weld. Since we've done the solution, we will go over the beam result and beam diagram, and also stress displacement, let's say distribution over the object. And then we going through the belt check report and see the design we have is withstanding the load as we desired. Alrighty. So let's start with the definition of fluid structure interaction. FSI is basically the interaction of some movable or deformable structure with an internal or surrounding fluid flow. Well, because everybody on Earth is submerged to a fluid called air, and also within human body, we have, let's say, an enclosure, which is our arteries, veins, and everything. Well, there is a high interaction between the blood and the structure of the, let's say, artery. This brings us a very important class of computational model with wide range of application in civil engineering, in biomechanics, in turbo machinery, and also in aerospace industry. Therefore, it is very important to understand how we can do this matching and how this analysis should be approached and what are the different methods and what we can get from each method. Alrighty, we have two main approach for FSI problem. The first is monolithic approach. Well, we have one specific software. Well, it's solving the structural domain as well as fluid domain simultaneously. We have one single software, and the good thing about this one is that when a fluid is moving or deforming your structure and new fluid domain is generated, this type of solver can regenerate the mesh and update the fluid domain after the structure is, let's say, deformed and updated itself. So this scheme also called two-way FSI. Well, two domains are solved at the same time, and they are simply getting their updates, and all results are pretty realistic. Different method is partitionized method. Well, the equation of governing the flow and displacement of the structure all solved separately. So you have a flow domain, you will solve it, and then you have the fluid forces such as pressure or shear to be transferred to the structure, and separately due to that forces, you solving the structure. And this scheme is not getting back with the update of the structure and refresh the fluid domain. This is also called one-way FSI. Both of them are valid, let's say, schemes. In most of the application, we are using two-way FSIs because the structure is deforming or displacing significantly. But for some applications, such as a wind loading on a big structure, we can assume that we have a steady state sort of flow in any direction, and it is keep continuing, and we can simply get the response of the structure due to that wind load, and there is no oscillation or, let's say, other issues with that one. In SolidWorks, we just can do one-way FSI. And basically, what we do have is first we are performing a flow simulation to get the flow distribution. We do have result exchange to any FEA study, such as linear or nonlinear, static or dynamic, either frequency, buckling, or fatigue study due to that loading of the fluid. And then we will review the result. However, one addition I would like to say, when you're performing any structural studies, you do have the option to save your deformed geometry and then bringing back and set up a new fluid result. So as you can see in a video, the flow distribution and its force on the structure is going to transfer over the let's say our structure, and we can definitely look at the displacement and deformation and if we are running any let's say nonlinear studies at any time step, we can let's say save a deformed shape and bring it back for a new flow analysis. All right, now with that explanation, let's have a look to our case study. We have telecommunication antenna on a structure being simply assembled, and it is going under the wind load testing. So first of all, we have a wind tunnel. As you can see, this is the box with a size of 5 meter to 3 meter by 3 meter. And also the model is located at the center of this tunnel. We have 3 communication antennas at different angles. So basically at 0 angle, then 120, then 360. We're assuming we have a wind flow at 12 meters per second in X direction. And then we would like to see if the structure is withstanding such a loading, either if the wind load is changing. We are going to resemble the change of the wind load direction by rotating our model from 0 degree, 15, 30, 45, 60, 75, and 90 degrees. So basically, we're rotating our model while the wind load is, let's say, coming from the same direction, and looking at the structural response at each point. In this regard, we will going to introduce our global goals on dynamic pressures, also velocity, resultant normal force and shear forces of the components. Make sure we are getting accurate answers. And also we are introducing one specific goal, which we call it equation goal, and we define it as let's say equivalent cell area, which is a fraction of your drag force on the actual component. And basically this is what we would like to trace and monitor or review at the end. So there are some global parameters we will follow, and there is one specific parameter we would like to look at the result on. So we are going to define both of these, and since we have completed our let's say result on the fluid side, we will learn how we can export the pressure and shear on the structure to a new FEA study. After that, we are going to look at the structure. Well, as you can see in the picture, we have different components, beam on these connector types, solid on antenna model, and also shell, well, the whole thing is fixing on. We are introducing solid, shell, and beam elements, also bringing the importance of having local contact set and different connector types such as edge weld connector, and how we can see the result. In this case study, imported pressure are coming from the fluid side. We have a fix on the shell here, and we have the edge weld with size of 0.25 inch, which is connecting this shell to that revolve component. All right. Now it's the time to look at the case study. Let me switch to my case study and bring this one to the screen. As we said, here is our model. We do have the stand as a multi-body component, and we can review what we have here. We have some beam elements, weld profiles, these three objects, and also we have some solid objects like this one, and I've did it on purpose. Although it is a beam, I haven't created using our weldment profile to show you how you can assign a beam even to a solid structure. And also we do have more, as this is the solid revolve part, and we do have this shell. Alrighty. From this point, since we reviewed in, let's say, stand, we do have the antenna unit and its local patterning. Now, the first thing we have to do is to create a fluid analysis. How we can do, as you know, simulation and flow simulation, both of them are add-ins in your SolidWorks, and dependent on license, you can activate them here and also here. You can see. Then, since you've done the activation, you will get the simulation tab or flow simulation tab. With the flow simulation tab, always be using a wizard to complete or create a new flow project. Clicking on this one, give it a name to the project you like, using any configuration if you like. Then next decision is about what is the unit system. So for example, SI, and if you like to modify any of this unit, for example, temperature to be in Celsius. And then from this point, we're going to our major section, which is the decision about the analysis type. A flow over an object, external. A flow inside a domain, internal. So in this case, we have external flow. For those who are really interested on doing heat transfer conduction to be considered, they have to tick on. And if just conduction, not radiation or convection, this second tick should be go on. Also, you can add radiation if you like. You can add solar radiation in this stage and go over the definition of the location and the other parameters, as you can see here. We can have time dependent. So either if you are interested on the final answer as it's become to an equilibrium, or you would like to look at the time frame or the time dependent analysis from 0.0 to after 1 minute, 10 minutes, 10 hours, and etc. You can activate the gravity if you like in any direction. And also you can have a rotational region inside your flow domain. Simply means if you have a fan and the fan is not just as an entry of flow, it is a rotating region with its blade, and you will tell the software there would be a subdomain inside your domain which is getting rotated at some certain velocity, and etc. And you are interested to look at the distribution of the flow around the blade as well as the whole domain. So by ticking any of those options, you will activate a new set of, let's say, parameters to be added to your simulation setup. So in this case, we just have an external flow, heat transfer not considered, no radiation, time dependency no, no gravity and rotation. Next stage, what you have to do is to decide about your working fluid. Well, in this case, in a category of the gas, I'm selecting air to be my default fluid. You can see we have more categories in liquids, non-Newtonian liquids, compressible liquid, real gases and steam. Well, all this information are coming from our, let's say, material database. Well, it's a very, let's say, good point of using SolidWorks simulation. Well, it's lots of data and on-shelf sort of components, and their data is being simply stored there. Flow type could be laminar or turbulent, or and turbulent. Here you can see laminar, turbulent, or laminar and turbulent. You can have high Mach number, supersonic flow, or you can also add humidity if you like. Well, these are not the case study for our model. And then you have to decide for your wind tunnel, is there any interaction between this surrounding fluid regarding to heat transfer? So if it's adiabatic, that means it is simply isolated, or either you know that it is there is a heat flux, heat transfer rate, or a wall temperature around your domain. Also, you can assign roughness. Next stage, well, we have to say our domain is initially at what sort of condition. So that is initial and ambient condition tab. First of all, the thermodynamic parameters, and we do have a domain at atmospheric pressure and temperature of 20 centigrade. Velocity inside the domain is right now, it is simply saying 000 meter per second in X, Y, Z direction. Since we have defined our problem to have a 12 meter per second velocity coming in X direction, and it's an external flow, so we can say our domain have a 12 meter per second speed at in X direction. For the turbulency, you can have more controls here, change the turbulence intensity length model to the energy and dissipation scheme, and also setting up the turbulence intensity and turbulence length here. In the next stage, well, before we finish the setup of the project, you are simply deciding about result resolution. One is very low resolution, 8 is very high, and simply it is going to change the mesh, change the setting, and change the precision of the calculation from 1 to 8. Well, basically, let's accept number 3. However, more details and more controls about this is also available. If you are interested, we are highly recommend to send us the question or attend to our flow training module. As I finish this creation, what is happening, I will have a flow tab and I will have a study called wind load, and simply this is what I get. I have two sections, input data and result section. Input data is where you completing the setup or the pre-processing stage of the project. The first thing you have to know, if you would like to get back and change the general setting, like the steps we go, either the flow analysis type of the flow you have, wall condition, or initial condition, you definitely can do that here. Also, if you are interested to look at the units and change the units here, also you can access it. You can also go back here and look at your component control. Means simply by tick and untick any of these components, you will include or exclude them from the flow analysis. And that is one other good thing we have in SolidWorks. So you don't really need to go and suppress the, let's say, model or the components. You simply tick them off and they will not include in your calculations. The first thing you will see in fluid setup is where your wind tunnel is look like. Here it is. Computational domain is the size of the domain where all the calculations are happening, or in other words, this is our wind tunnel.
Simply, you can see it is X, Y, Z direction. You can simply use the handle to change them, or either right click, go to edit definition and say I would like to change my wind tunnel in X minus plus, Y minus plus, and Z minus plus. One other good thing you can do in this case, if any XYZ you go, you can say there is a symmetry. Means exactly the same model is repeating on X plus direction. That is very good since you might use a symmetry in your simulation and you would like to reduce the calculation time. Also, you can say there is a periodicity, means it is going to repeat it a couple of times here in our domain. If it's not the case in this in your study, then you simply have to accept it as it is. Also, you can do a 2D simulation by making a slice of your model, and again, that could be valid if you have a symmetrical flow, let's say, distribution over your objects. So, at the first instance, we have decided about our wind tunnel. Well, inside this wind tunnel, the initial conditions are simply governing. We have atmospheric pressure, we have 20 degrees of centigrade of temperature, and also we have 12 meters per second of wind flow, which we said it is air coming here. That is almost setting up our case. You have more options. If you are going to internal flow, then you can assign boundary condition such as your inlet mass flow, volume flow, or velocity, and using any phase you like, and also the outlet condition. You can do a pressure condition on any phases. So simply selecting a phase and saying it's environmental pressure, static pressure with the value, or a total pressure with the value. Turbulence parameter and boundary layer can be also controlled here. Well, again, this is not the case for us. And the last thing, when you are having, let's say, wall, well, basically it's an object. On each wall, you can say it's a real wall, or we do have ideal wall. And also if there is a motion on your wall, for example, if it's rotating, then you can say what is my translational velocity or angular velocity in that wall. All right, well, this is not our case, and simply let's do not go over it. However, the flow software got so many other capabilities, and you can explore it in, let's say, our webinars, the other webinars we've done, and you simply can access it and look at the different sort of capability of it, like electronic cooling or rotational region, and etc. Well, this case is simply considered a wind tunnel as we set up with the 12 meters per second in X plus direction here. What is very important, we always trying to achieve the optimized simulation. In this regard, we have to make the software to trace some parameters which are very important to, let's say, calculate and do a very precise calculation on them, and also making the mesh resolution as it's suitable. This is coming to a series of goals you are simply defining. If you are interested to look at the convergence and variation of a parameter, then you can right click on your goal. So either it is globally you would like to trace it, or at the point, or at the surface, or over the volume. Also, if you have your own equation to be traced, then you can insert the equation code. This is exactly what I've done. I would like to make sure the dynamic pressure, velocity, shear stress, and force over the whole structure is fully converged, and I would like to trace them. Simply, I went to a global goal scheme and select my parameter. For example, dynamic pressure, its minimum, maximum, or average values. I can select multiple and then say I would like to create a goal. And this is exactly what I've done to create dynamic velocity, shear, and force on my domain. Now, if there are some specific components, I would like to trace any specific parameters on them, then I have to go and insert a surface goal. For example, I would like to look at my antenna and I would like to trace the force on them. So simply force, tick on, and this time it is my antenna. Or this selection could be also a single surface like this one. So either you're selecting the whole component or selecting a face to trace the values of the force. All right, so if you look at what I have done for the setup, I'm saying force on each antenna component is what I've simply interested to trace. Now it's the time. Drag coefficient, or ESA, equivalent surface area, is not in the list of our parameters to make a goal on them, either on a global scheme, surface, or volume, or point. Therefore, since the formula, let me bring back the slide for you guys. Here it is, hopefully. Since I would like to create my own formula here to be traced, ESA simply defined as the force divided by 0.5 times density velocity square. Well, it is equal to drag force times, let's say, effective surface area of the antenna. This is not a parameter in your list, therefore I have to create an equation goal for that one. So back to the software, and simply I'm inserting an equation goal. Well, I'm recalling my force from here divided by bracket 0.5 times density which it's 1.225, I believe, for the air, times velocity, average velocity square. So simple as that. I have defined my equation to be traced here. Look at this one. Let me close that one. And this is exactly what I've created. Selecting the force divided by 0.51225 density of the air times global average velocity. Now the question is, all right, this is a constant density. What if the density of air is changing and I would like to insert and make sure at each iteration I would like to have an update on the density of air and to be inserted there? The answer is simply, let's go, make sure you inserting a global goal, and this time you tracing the density of the fluid. Since you're creating that density, then again you can recall it in your equation goal. So what we understood, there is a big list of the parameter. Well, they can separately be traced. If you have a specific formula to trace the result on, then you have to use any of these specific, combine them using the mathematical operation to create an equation goal. So effective sailing area on 3 antenna units is what I've selected and I have created. So SG force 2 regarding to the second unit, and SG force 3 is calling for ESA 3. All right. Now with this definition, what we have, we are going to do the calculation on a simple case study. Well, the antenna is positioned like that, as you can see here. Let me bring the normal. And then simply what I do is I'm tracing the dynamic pressure, velocity, shear stress, and force on the structure as a whole or global goal, as well as for specific antenna units, I'm tracing the force, and I've created my equations as ESA 1, 2, 3 using the global or surface goal as I've defined it before. All right, so that would be the base study at this angle. Well, you can simply look at the results and see how does it look like. However, this said, we are going to have different angle on this case study. Well, the whole antenna unit and structure is simply rotating from its position as 0-degree lock, that one, up to 90 degrees. So what we need to do is very simple. You go into your project, right click and say, I would like to run a new parametric study. When you're doing that, you're simply getting the access to input your variables and look at your output parameters. In input variable simply means you have to select what is going to vary. Could be your dimension, could be any, let's say, parameter from your flow study. Simply, if you go here and set add simulation parameter, for example, you can go to the general setting, go to initial and ambient condition, and select the X direction velocity. And it's showing you right now it has the value of 12. Then you can click on it and say, I would like to vary it from, let's say, minimum of 1 to maximum of 20 with the step size of 2. That is one thing you can do. Similarly, you can pick up any dimension if you like. So simply, you're going to your model, pick up a dimension if you like to see it, or even accessing to your model and go to your mates, and this is the angle definition, and I'm picking it up. Simply by clicking OK, I'm telling the angle of the assembly between these two plates are 0 at the moment, but I would like to change it as 0 up to 90 and step size every 15 degrees. Simply clicking OK. So I will have the design points as 0, 15, 30, 45, 60, 75, and 90. What will happen? The software will go and change all this angle with all the conditions you have defined on the base project. It's going to run it, and then on the next tab you have to say what I would like to trace. You can simply trace your goal by say add goal and say I would like to trace the ESA and forces. This is all I would like to trace on. Either you can go and add results. If you are defining any, let's say, cut plot, any, let's say, tracer study, any other sort of plots in your, let's say, result section, you can simply recall them here. We will go through this later on, how you can define that. Simply using the cut plot and saying OK. Then in a scenario, you can see you have created 6 scenarios from design point 1 to design point 7. Well, the model is going to change the angle from 0 to 90 degrees, and it's going to indicate or record the result of the force and ESA for all these 3 antennas. Now, this is the time and it's ready to run the case. If you run the case, then starting with the design point 1, 2, and 3, and continuously it's going to, let's say, change the angle, solve the model, and simply bring the result. Let's not do that because it's taking time and we are not wasting our time. Let's look at what we have and what I've simply defined. Following the same procedure, attack angle, you can see the only parameter I've changed is the assembly angle, where it's going to rotate my assembly from 0 to 90 degrees. I'm following up the ESA and force and also the cut plot. My scenarios all being calculated and I can see all the results here. All right, so simple as I would like to look at the result. For example, the total force on the first unit is recorded as 12.54 Newton average. Second one is 20.48 and the third one is 26.23. Similarly, all this ESA simply being calculated. So one by one, that is being calculated and being updated. Now, if you like to compare these results here, you're simply going to the goals tab and you can ask for a summary of them or history of them. History, for each goal on a design point, you will have the history plot. For the summary, you will have the variation of each goal over different design points. For example, when the antenna is rotating, the force on the first antenna unit is changing like this. And either that is acceptable or not, that's your decision from this point. So you can see all these ones are simply getting created. Force 2, force 3, and also ESA 1, 2, 3 is all here. Also, we said there are some cut plots. Well, it is showing us the result on the structure. Well, you can see all this is being updated and calculated. So just clicking on any of them, I can simply review. This is the flow distribution over my object in design scenario 1. I can close it and look at the second one. Here it is when we have a rotation. Alrighty, guys. Now, what we've done 6 different design points from 0 to 90 degrees, and we simply follow up their trend. And also, if you are interested to look at the result on a specific one, then we have to cancel this and come back here, load our result, and simply looking at the result section. We're calling the .fld file, which is the result file, and simply the first thing is to insert a cut plot, and you're telling I'm going to cut based on front plane, contours of velocity. Well, at the same time, I would like to look at the streamlines of the flow. Here is the velocity and how the streamlines should be set up and what are the setup parameters, for example, length, scale, width, contrast, and density of them. Simply by clicking OK or say show, you will look at your first cut plot. Let's look at what I have created. Let me show this. And this is exactly the cut plot I have created. So you can define the cut plot even before you do the solution. And in your parametric study, simply recall and record all the images on here. Cut plots could be at a specific location. By right click, you can definitely look at the variation from top to bottom and see how the fluid result look like in a different location according to that cut plot. You can activate multiple cut plots here and simply adding more. So stop this one. I'm going to my cut plot, insert a new one, and then this time I would like to have on top plane contours of velocity, streamlines of velocity. And clicking OK, I will have 2 cut plots. Well, again, you can play more animation and look at the other things. So since our focus is not about post-processing of this flow simulation, let's stop at this point, but you can do more. As surface plots, you can do ISO surfaces, flow trajectories, particle studies, or evaluating any parameters on a point, surface, volume, and etc. So it looks that we simply finish our flow setup here, and we are ready to set up or transfer or exchange the result to an FEA software. Let me hide these two, and I'm hiding my computational domain as well. Well, this is the model. All right, now in order to transfer the result, it's pretty the same procedure as you go to your simulation tab and you're creating a new study, and you're simply deciding what sort of study I would like to take. Static, thermal, frequency, and etc. Again, disactivating or deactivating this, let's say, icon is highly dependent on the type of license you have. Let's create an static study and clicking OK. Well, I'm simply doing that. Now, the main thing is how we are recalling our fluid result. In order to do that, the first thing is go to your study, go to its property, and simply go to flow thermal effects and say flow pressure option, include the flow pressure effects from SolidWorks flow simulation and recall that result. One thing for sure, this is the last iteration we have. If you like to access the other attack angle result, there is a parametric study folder. On each subfolder, you can see there is an FLD file. You can simply recall it. So it is one, or it is my other attempt if I would like to access. So let's go back here. One FLD. So, okay, so come back and parametric study, or let's go to, I don't know, my 9 attempt, which is nothing on it. Let's go to the third one, and this is the third flow. So it is basically not 0, not 15. It is the third attempt, which is 30 degrees. So we can simply recall any fluid result as you might like it. Where we started, simply again, I'm repeating, I'm going to my study properties, go to the flow thermal effect, and then simply I'm recalling my flow result on each variation or the final answer. Simply open, and you can see the flow iteration number is 70, the last iteration, and using the reference geometry offset in the file, which is what we have defined in initial condition, atmospheric pressure, or define a reference pressure offset as yourself. By clicking OK here, you can see your external loads folder has been updated with fluid pressure, fluid shear stress in X, Y, Z. Right now, there is a link has been established. Result has not been exchanged. In order to do that, one more step we need to do. We go to in Tools, Flow Simulation, and go to the Tools and export the result to simulation. When you're doing that, all these let's say, forces or external forces are getting updated, and you definitely can look at their plots. All right, so you can go here, and right now, because the model is not solved, you can simply just edit the definition and simply look at the different, let's say, time step. Since we have done this, the rest is simply following the same procedure as we defined the studies in our simulation, starting from the list of the parts you have, and then decide which one is solid, which one is beam, which one is shell. Well, basically, you can see these 3 components as being created using development, let's say, module of SolidWorks is automatically converted to a beam. Here it is. You can see the beam icon on them. However, as this component has not used development module, it is now looked at solid. In order to convert it to a beam element, right click on it and say treat as a beam. When you're doing that, your component is showing as a beam. Okay. Now, what is very important in, let's say, this setup, when you have a beam, you have two endpoints, and this is called joints. So always go and edit your joints, and simply this is what you can show. We have a joint here, we have a joint here. Each component got a joint. You can simply select all your components, recalculate them, and make sure you're creating enough joint as you might like it. So point 1, point 2 representing the solid bar, and these 2 points are simply creating the next one. So if you're happy or you would like to make more or less joint by changing these values. So simply cancel and let me re-edit the joint and say select all, calculate, and make sure it's all the joints, and it is simply the connection between the parameters as we have. Clicking OK, and I do have my joint group. Let's specify the material. So all material, for example, I would like to use plain carbon steel for them, apply and close. The next thing we have to do is to simply make sure we have a connector between this shell and between this material. Since we said this is shell, as it is showing me a solid body, I have to right click on this and then say define shell by selected faces. That's how I'm converting the actual component from a solid model to a shell model. Clicking on the face and then give it a thickness of 10, and you can see that is how the face is getting offsetted. Now I can go to the offset scheme, make sure it is located in the correct direction. So the offset should be, the thickness should be 5, and right now the orange and the green planes are simply showing us the thickness of this shell. So clicking OK, and I've converted my model to a shell here, solid here, and beams on here, again solids on the other components. Alrighty guys, now material setup, beam joints are set up. We have our decision about different type of let's say element, solid, shell, and beams. In order to check if everything is correct and defined in right order, you can always go to your mesh, right click and create mesh, either make it fine or coarse using standard or curvature base, and either high quality or draft quality mesh, and clicking OK. You can see my model is perfectly getting meshed, and simply these are beam elements, this is solid element, this is shell element. So I have no problem with meshing. Again, like from the flow side, and here is again we have a very important topic of having a very good mesh to converge the answer and capture all important effects. Well, that would be a very separated topic, and we are not going through this, and we accepting everything here. But one thing for sure, our mesh should be perfect, means optimize, not very coarse, not very fine, and it is capturing all the important events happening in our structure. One thing you might know it very well when we're talking about 3 different element types, such as solid, shell, and beam elements, they have different degrees of freedom. Solid elements basically have 3 degrees of freedom. Well, the shell and beam, as they are 2D and 1D elements, they have 6 degrees of freedom in order to mimic not just the translation, but also the rotation. Therefore, when you're having a solid attaching to a shell, you might create a hinge connection, since you might simply bond these two components with their translational degrees of freedom, but since the other one, or the shell one, or the beam one, has 3 more to simply be bonded, they might create a hinge connection. Therefore, in all these cases, when you have solid attaching to a beam or a solid attaching to a shell, since they have 3 let's say rotational degrees of freedom more than solids, therefore you have to go to your connections and make a contact set between the parameters. Okay, simply selecting the face, for example saying bonded, I would like to do a bonded connection between the joints of this element to the face of that antenna unit, and clicking OK. That is something very important. If you don't, then the contact, which is a bonded contact between these two types of elements, either not getting established, or you might create a hinge connection and this can simply rotate against the beam element. That is something that needs to be done in order to complete the process. All right, let's have a look to the study I've created. Well, following the same procedure, and you can see all my contact sets locally has been defined between the antenna units and the beam structures, and also with the vertical bar and the revolved section, and also between the shell and the revolved section. So all the local contact set has been defined. Just to edit definition, look guys, phase 1 to phase 2 of the revolved section. So this is a very important step to take, and make sure you're doing all correct. Then on the next stage, you have to decide about the connection type. Well, we said there is a weldment here between that shell and the solid. What I have to do is simply right click on the edge weld, select the face of the shell, select the face of the solid, and then simply say what I would like to have as an edge, intersection edge. For the weld sizing, you can either use American or European with the electrode type and give it a safety factor or estimated weld size, and simply clicking OK to create your first edge weld here. Looking at my connector type is simply I do have an edge weld at this point. All right. And the last thing I've set is simply I've set up a fixture around that edge, fixing my shell here. My setup is simply completed. Just as an overview again, parts and their material, joints for the beam, any connector such as edge weld, then local contact set since we are using different type of elements, and then fixing the edge, and then exporting the flow result and import it here in our FEA. First is our study properties to establish the link here, and then also go to our tools, flow simulation, and make sure we exporting the result to the simulation connection, and then validating the connection. All right, now we are ready to go. Simply by clicking on run and finish the study, you can simply look at a couple of things. The first thing is what is being imported. Right click, show the plot. That is all the pressure. Hang on a minute, so I have to export it again. I've simply messed up with the other study. So let's go to flow simulation. Let me close this. That would be much better. Do not save, and let me reopen it. Since we have introduced a lot of changes. All right, so show the plot. Okay, looks it's all been updated and saved. All right, let's go tools and export the result to simulation. Make sure it is all updated here. And let me run this study quickly and then look at the results. All right, no loads. Okay, perfectly not working. All right, I have to make sure this is not save, and let me reopen my model. Alrighty, let's load my flow results. It's all good. Coming back to our static study and looking at this one. All right, so I do export. The result and make sure my connection is established. Here it is. Okay, clicking OK. All right, let me recall it. Here it is, and open. Clicking OK. Run this study. All right, now it's solving. Sorry guys, my connection has been simply lost. All right, the first thing, the fluid pressure. Show the plot. I can see what is being imported here. So that is the fluid pressure at the last iteration, and you can see this fluid pressure imported here. Also, you can look at the shear stress, X direction, shear stress, Y direction, and review what is being imported to your structure from the fluid result. That is the first thing you can do. Second, you are going to your results section. So you can simply review the stress values on the, let's say, solid part. Well, obviously it's showing us much less than what the yield strength is look like, showing us some stress concentration on those locations. So you know when you are doing stress analysis or FEA analysis on mixed shell and solids and shell stress plots are showing as it is, then you can definitely go and modify to look at the stresses on the beams by selecting that one. And if you just do, this is exactly what I get. And you can see the axial and bending stress values is what I'm checking here. You can edit definition this one, go and select, for example, bending, torsional, shear, and everything else on your beam results. So the first thing is the stress. So either on the beams or on shell and solids. Second, it's the displacement. Well, it's showing everywhere. And if I do the animation here, it's simply showing me the structure is going to have 0.3 millimeter of deflection, and it is animating, or let's say doing it in that way. Okay. The next thing which is very important for me is to go and define a beam diagram. Well, I can, for example, go and check one of my moments on this beam to be shown. If I do click OK, what I will get is the beam result, as you can see here. So that is the moment about direction 1 on a specific beam like that. You can definitely modify that and select more beams to show your result on. So beam diagram or beam stress. Also, you can review the beam forces or stress values for all the beams, if you like, from 1 to 5 beams I have, and clicking OK, and you will get the list of the forces. It is showing us the values of the force on each node of the beam. You can filter it by just showing the extreme values only, and say, for example, beam 1, the extreme value on beam 1 or component 1 is that, beam 2, beam 3, and beam 4. So either you're reviewing the forces or stress values is what you can do. So stress as a general, stress on the beam, or beam diagrams. The last thing I would like to show is our weld. So right click and go to the list weld result. It is basically showing us and suggesting us the weld size, the weld throat size, and joint normal force, shear weld axis force, shear surface normal force, and bending moment values. You can definitely make a graph out of these values and look at the weld size when it's positioned, so around this circle, and look at what is suggested. So either you take the mean values, max values, or anything else. That is your decision here. Alrighty, guys. So as you can see, all the results from the flow is simply brought here. We set up a new study, we done the mix elementing, and we simply reviewed the result on individual, let's say, beams, shells, and etc. Alrighty, so let's wrap up our let's say section. Well, what we have experienced from this point, we went through the different flow result and we learned about how we can compare a cut plot or a goal in our flow results, make sure everything is fine there, and then export and exchange the result and simply recall it and simply look at the structural stress, beam stress, displacement values, or beam moment diagram. Also, we can have a weld check plot, look at the variation of the weld size around its geometry, or listing all the components we have here for the extreme stress values or force values. Just as a wrap up, flow simulation is an add-in. Well, it can do multiple things as internal, external flow, heat transfer, and any other application. Also, it could be specifically go for electronic cooling module and HVAC studies, where you're accessing a very large and huge database of the material in our flow simulation package. And doing any study of this one can be simply linked to our FEA package as well, where you have your CAD parameter, you have the flow study, and we do have the structural response here. Well, you can either use a linear static studies or the capabilities of professional as frequency, thermal, buckling, or drop tests, are also accessing linear or nonlinear dynamic studies here. Alrighty, guys. So if you have more commercial discussion or questions, please contact John Belsham at john.belsham@intercad.com.au. Or if you need more technical information or any specific information on how step-by-step those things more in detail, please contact me, svandiar.kuhi@intercad.com.au. I hope everybody enjoyed the session and hope to see you in the next webinars. Thank you so much for attending and have a good day.